This project focuses on giving an exposure to the role of proactive caching in 5G network. It is based on the paper Event on Edge, the role of proactive caching in 5G wireless networks, and the presentation is prepared and presented by Li Jinya and Yuan Xichen. In this presentation, we will introduce some background information about 5G, followed by an explanation of the concept of proactive caching. After that, a detailed elaboration is given through 2 case studies, and this presentation will end with a summary. In the past decades, human has experienced an evolution of mobile communication starting from 1G analog mobile generation with data rate up to 2.4 kbps. At that time, it is only possible to make a voice call using cellular phone. Now, we have 4G true mobile broadband with data rate up to 100 Mbps. People are able to watch video, browse websites, and social networking on their smartphone. So, you may ask, what's coming next? Well, according to the paper 5G Radio Access Research and Vision, the next generation is 5G, coming with very high achievable data rate, very low latency, and very new technologies to solve challenges the ping traffic demand it brings with. The need is raised by the continuously growth of usage of mobile smart devices on global traffic. As shown in this figure, the total mobile traffic is predicted to grow tremendously in the next few years with the increasing usage ratio of smart traffic. According to forecasts from Cisco's Video Networking Index, overall mobile data traffic is expected to grow to 24.3 exabytes per month by 2019, nearly a tenfold increase over 2014, with exponentially increasing demand for wireless data traffic in recent years. According to the paper Big Data 3, it is infeasible for current cellular system architectures to satisfy gigabit-level data traffic in a cheap way. This new phenomenon has urged mobile operators to redesign their current networks and use more advanced techniques to meet the traffic demands with low cost and faster speed. One of the solutions is the small cell network, which is densely deployed by self-organizing, low-cost, and low-power small cell base stations, or SBS. This is the system model of a popular design of 5G scenario involving SBS from the paper Proactive Caching in 5G small cell networks. Small cell networking is a new paradigm based on the idea of deploying small range and low-cost small base stations. Those small cell nodes connect to broadband via backhaul link, and the central scheduler is in charge of providing broadband connection to small cell nodes. The small cell nodes serve user via small cell link. Each user is connected to its small cell node via a wireless link and its neighbors via D2D links. The existing network paradigm for such a system is reactive. What is the meaning of reactive? For example, if the user requests for a file, the request will be served upon arrival, therefore the request will go through small cell up to broadband to get the file and send back to user. During 5G network, the request is so frequent and the stream is of very high volume. Therefore, the reactive paradigm will bring the problem of falling short of solving ping traffic demands with expensive installation and backhaul cost. These shortcomings are said to be increasingly acute due to the surging number of connected devices and the advent of ultra-dense networks, which will continue to strain current cellular network infrastructures. Based on the idea that information demand patterns of mobile users are, to a certain extent, predictable, the problem we have discussed is addressed by a new proposed network of proactive caching. It is introduced in the sense that it could predict what file users need and store it either in a cache of a station or in user's device. Therefore, if the user requests for a file, he does not have to get the file from broadband. Instead, he could find the file either stored in a small base station or user terminal if the file is pre-stored in cache, and the file will be sent back to user. Therefore, the backhaul traffic is significantly reduced, and the problem caused by high traffic, such as congestion, is solved. Next, we'll present the effectiveness of proactive caching with two case studies. These two case studies take different approaches to store files. For case study 1, proactive caching reduces backhaul cost by storing files in those base stations. The files are not just any files, but those most popular files that are more likely to be required by users. In this way, it reduces backhaul traffic as users can just get files from cache. So you might ask, how to design popular files and how to store them in base stations? Well, the proposed procedure consists of two parts. The first part is training. The second part is placement. In training part, it aims to estimate file popularity, and in placement part, it stores those popular files in cache of base stations. The popularity files is estimated by building a model over popularity matrix, PM by F, where M stands for users and F stands for file. The value of P of the user file instance stands for popularity measured by least square minimization method based on already available information regarding users' preferences and ratings. The placement procedure is to store files based on their highest popularity according to popularity matrix we retrieved in training part until storage capacity is achieved. It follows a greedy loop to store most preferred files of each user as shown in pseudocode below. It loops over files and users to greedily store files in cache until there's no more storage. Here is a performance curve compared between reactive paradigm and case 1 proactive paradigm. Reactive paradigm is represented by diamond curve and proactive is in dot curve. We consider three parameters: number of requests, cache size, and distribution parameters. Both high and low situations are considered. Our main concern is backhaul load and satisfied request. Backhaul load represents traffic in backhaul link. As for satisfied request, a file request is said to be satisfied if the delivery time is below the threshold. The first set of performance curve is related to user request number. As the number of users' requests increases, the amount of satisfied requests starts decreasing due to the limited resource constraints. However, the proactive caching approach outperforms the reactive one in terms of satisfied requests. On the other hand, as users' requests increase, the proactive approach tends to decrease the backhaul load, outperforming the reactive approach. The gains become constant after a certain point. The second set of performance curve is related to cache size. As cache size increases, the number of satisfaction approaches 1, and the backhaul load becomes 0. This reflects the extreme cases, where all request files can be cached. For intermediate values of cache sizes, it can be seen that proactive caching outperforms the reactive one. The third set of performance curve is related to zip parameter, and some files become more popular than others. The gain between proactive and reactive caching is higher in all load region. In addition, the gain further increases with higher incoming loads in terms of both satisfied requests and backhaul load. For case study 2, proactive caching reduces backhaul cost by storing files in influential user community formed by user devices. Therefore, if the requested file exists in neighboring D2D caches, the user is simultaneously served from the SBS and its neighbors according to availability link capacities. In result, backhaul load is reduced and the satisfaction ratio of user will increase. A similar question arises: how to design influential user and how to store files? Well, the proposed procedure consists of two parts. The first part is social community formulation. The second part is social aware caching via D2D. In first part, it aims to detect influential users and form a cluster or community, and in second part, it determines content dissemination process and thus store popular files in the community cache. For the first part, social community formulation consists of two steps. First step is to detect influential user based on edge vector centrality, which estimates the influence of nodes in the network by using the edge vector corresponding to largest edge value of adjacency matrix of the network. Second step is to form social community by applying clustering method to influential users. For the second part, the social-aware caching via D2D also consists of two steps. First step is to determine content dissemination process. The purpose of this process is to determine file popularity in each community. This process is modeled by Chinese Restaurant Process, or CRP. The basic rules are described in detail in article Bayesian nonparametrics. In this model, the probability of a customer to choose a table is affected by the number of occupants to each table, and this is the popularity function. It can be seen that the decisions of subsequent customers are influenced by the previous customer's feedback. The CRP makes a good model to simulate the content dissemination process of social network, where user as customer and files as table. This is the reason why we interpret the content dissemination process in social network by CRP, where the decision of subsequent users selecting a files are influenced by previous users' selection. The second step is to store files in cache in user device community. The placement procedure uses similar algorithm as case 1, where storing is done among most popular files greedily until no storage space remains. The evaluation matrix is similar to case study 1. The difference is that we use the small cell load instead of backhaul load to monitor the traffic. The small cell load is the amount of small cells bandwidth consumed by the user over the total consumed bandwidth. The first set of performance curve is related to user request number. As number of requests increases, the number of satisfied requests decreases rapidly, while the small cell load decreases at a very slow pace. The proactive caching approach outperforms the reactive approach in all load regions. The second set of performance curve is related to cache size. As cache size increases, the gains of satisfaction increases and backhaul load decreases nonlinearly, and proactive outperforms reactive. The third set of performance curve is related to CRP parameter. CRP parameter represents number of distinct files. Where CRP parameter increases, the number of distinct files also increases. The satisfaction and backhaul load become approximately constant in the reactive approach. The proactive approach has better performance, but it gets closer to the reactive one as the parameter grows. In this project, we discuss the limitation of current reactive networks and propose a new proactive networking paradigm where caching plays a crucial role. By exploiting the predictive capability of 5G networks, coupled with notions of content awareness of social networks, it is shown that ping data traffic demands can be substantially reduced by proactively serving predictable users' demands while caching strategic contents at both the base station and user's device. Examples and data proof are given through two case studies. This is a reference list related to this project. That's all. Thank you.